Okay, so let's get started. So, so the formulation. So, most of this course will be about supervised learning. So, in some part we're going to talk about unsupervised learning, but like I think maybe like 18 of the lectures will be about supervised learning. So this is about supervised learning. So let me just so we're gonna have some definitions. So input space. This is the data that you want to classify, or kind of like you want to do regression on. So, and there's a label space. Let's call it Y. And there's a joint probability distribution. P over the space of X times Y. And there's a, let me see how to I guess probably I will still try to do, maybe I should do this. I think this is better, right? So, we're gonna have some training data points. So these are x1, y1 up to xn, yn. Each data point is a pair of input and output. And we're going to use n for the number of examples, forever. So n is reserved for the number of examples for this course. And each of these data points, xi, yi, is assumed to be drawn IID from this distribution P. So P is the distribution we are interested in, and we have some examples from it. So, and we have some loss function. And this loss function takes in two labels. So, and it outputs a number that characterizes how different these two labels are. And I think typically the convention is that the first one is the predicted label. And this is the true label. Or this is the observed label. And you assume that this, if you have, the loss is always non-negative. I think in some cases the loss can be negative, but in most of the cases the loss is non-negative. And now you have, suppose you have you can also have a predictor, because this is what you are interested in. You want to have, or sometimes it's called model, sometimes it's called hypothesis. We're going to use all of this interchangeably. All of this, are used in some slightly different contexts, but they all mean the same thing. It means the function you want to look for to predict your label. So, so this is a function that's called h. It's a mapping from y to x to y, and you can define the loss of the predictor on example x comma y, and the loss will be, you first plug in h of x, which is your prediction, and you have y. This is the loss. And then after you define all of this, you can define the so-called expected or population risk or loss. This is kind of the interesting thing about machine learning. Like everything has like two names at least. I think 2 is a lower bound. Sometimes you need 3. So, and also like my brain is kind of like for different kind of situations, I use different name for this. Be prepared for that, just because like when I learn this part of the things, and those literature use that name, and then if you learn something else, then like those kind of papers use a different name. But so my brain just these names burn into my different part of my brain. So I might use inconsistent terminologies a little bit, but all of these are the same. Like they are the same. Like expected just means population, and risk just means loss. But of course, I will try to be consistent as much as possible. So, and this expected risk or population risk is defined to be the expectation of the loss. And here the random variables are x and y, and they are drawn from this population distribution P, and that's why it's called population risk. And this is your final goal. Your final goal is basically to minimize, so find H that minimize the population risk. At least this is the goal for the first at least 15 lectures, right? So like this is the goal for supervised learning. You just want to predict as well as possible. Okay. Okay. So so to achieve this goal, you also have to introduce more concepts, right? So one concept is this so-called hypothesis class. Sometimes or hypothesis family, and you can also call it predictor class, predictor family, model class, model family. So and let's call it capital H, and this is a set of functions from x to y, right? So and you can define the so-called excess risk, because at the end of the day, you're going to search over a set of functions, right? So, and maybe this set of functions is very bad. For example, this set of functions only contain one function. So that's why people define this so-called excess risk, which tries to kind of like define your error relative to the power of this hypothesis class or this set of functions, right? So this excess risk with respect to capital H. So this is defined to be your population loss or population risk minus the best you can find in this family. Okay, so basically this term is the best model in H. Which H? Sorry, the inf. Oh, yes. So this is a good question. So inf, basically you can view it as mean. I guess we just for this course, let's say they're exactly the same. So of course, they are not exactly the same, just because sometimes you don't have a unique minimizer, right? So you have a sequence of like you can like a maybe I'll have a post to explain the subtle differences between these two, but for almost, I think for exactly for this entire course, you can just assume inf is the same as minimal. Yeah. Cool. So, and this is larger than 0 because this is the minimum, and so that there's no way you can get better than the minimum. So that's why it's larger than 0. So in some sense, this is trying to kind of to think about excess risk is one way to kind of like only think within the family of H, right? So now if you get 0 excess risk, that means that you cannot do anything better within this family, right? Of course, if you change your family, maybe you can get something else, but at least within this family, there's no way you can do better. Okay, so this is the basic language we are going to work in for this entire course. Any questions so far? In any case, like just feel free to interrupt me at any point. You don't have to wait until I pause, in either the Zoom meeting or here. So some quick examples to make it less abstract. So this is, I assume this is relatively abstract. So one of the typical questions is regression problem, where your y, the label set, is real number. So they are continuous labels. And oftentimes for regression problem, you have the so-called square laws. So this is Ly hat y is equals to maybe something like half times y hat minus y squared. For example, if you want to predict the temperature, it makes sense to use the square laws. Of course, there are other different kind of laws. And another possibility is classification problem. So in this case, the Y is a discrete set. You have a set of K labels. Maybe it could be 2 labels, cat versus dog, or it could be like multiple labels. And then your laws, the final laws you care about often is this so-called 0-1 laws. So basically you say that if you didn't get the right label, then you are equals to 1, otherwise you are equal to 0. This 1 is the indicator. So indicator E is 1 if E happens, and indicator of E is 0 otherwise. So you'll see that when you really do the practical machine learning algorithm, you are not going to use these laws because of the other issues. But this is the laws you care about eventually. At least this is one of the laws you could care about eventually. This is the so-called accuracy or the error, right? But when you train it, you maybe use cross entropy. That's a slightly different question. So okay, so now this is the setup and the goals. And now let's talk about one important algorithm, which is called empirical risk minimization. This is the algorithm or type of algorithm that we're going to analyze for quite some time. So the algorithm is very simple. So I guess this is what you do in practice every day. So you have some training laws. Sometimes it's called empirical laws. And sometimes it's called empirical risk. So this laws, we use L hat. L hat means it's empirical. Every time you use a hat here, it's kind of like, it pretty much means empirical. So you have the sum of the average of the laws on all the examples, hi, yi, from 1 to n. And then you do the so-called empirical risk minimization, ERM, empirical risk minimization, where H hat is you find the best model in this family. I guess here I'm using arcmean. So arcmean and inf is just exactly the same for this course. So you find the best model within the family that minimize your empirical risk. And you can break tie arbitrarily, this kind of like we don't care about breaking ties, in many cases. And so this is the algorithm. So using this algorithm, you may need to use some other optimizers to find the minimum, right? But this is the abstract way of thinking of the algorithm. You'll find a minimum, and the key question is that how do we why this is a good algorithm, right? Why this is doing something sensible. And one of the key property of this is that one of the reasons why this is somewhat meaningful is, I guess, as you know already from previous classes, because xi, yi are ID from P. So then if you look at the expectation of the empirical loss over the randomness of the examples, right? So if you take expectation of the empirical loss of one example, let's say, and let's say the examples are random, then this is equals to the population, right? This is exactly the same as you draw xy from P, hx, y, right? To verify this is just a change of notation in some sense. This is L of h. So the expectation of the empirical loss is the same as so basically this is saying that if you take expectation of the empirical loss, L hat h, which will be an average of all of this 1 over n times expectation L h xi. Right, so this will be equals to L of h. And here the randomness comes from all the xi's and the yi's. Right, so this is the typical justification we have for this kind of algorithm, because the empirical loss is an estimate for the population loss That's why minimizing the empirical loss probably would lead you to minimize the population loss. So in some sense, at least a good part of this course is to justify more formally why this is the right thing, right? So intuitively it sounds right, but formally whether this is, like we want to kind of prove that this is actually the right thing. And it's actually not that easy because it does depend on some other things. For example, how many examples you have and how large your hypothesis class H is. It's not that simple. This is just a kind of like an intuition. Okay, so all right, any questions so far? And also we're gonna have, I guess, I assume that most of you know this. This is just a formal definition. So when you really do this, you have a hypothesis class. When you really do it in computer, you have to have a parametrized family, so you can optimize the parameters. So you can also have a parametrized family. So you call this H, for example, something like H sub theta, and where theta is in some space of parameters, and maybe let's say theta is in RD or some kind of like is the parameter. And then, for example, theta could be, so capital theta is the family of parameters. This is the, I guess, sometimes you want to say that you only do it for sparse parameters or only do it for certain kind of parameters. So, and one of the example of this is that you can take H to be, for example, H theta x, which is equals to theta transpose x. Then this is all the linear models. Okay, so this is easy. And then you can also do ERM for parametrized family. So I guess here, this is actually probably the most important cases because empirically you do parametrized family. And now your training loss, let's define this training loss still as L hat theta, as L hat. But let's, with a little bit abuse of notation, you say the theta is your input of the training loss, right? Theta is the parameter. Before we say the training loss is a function of the model, and now it's a function of the parameter because the model and the parameter are just one-to-one correspondence in some sense. Or maybe not one-to-one, but they have a correspondence. So your representation for the model is really through the parameters, right? So each parameter corresponds to a model, and this is just a, I guess I'm just writing what you're expecting probably. So this is the empirical loss, and here I'm overloading the notation a little bit, and we are going to overload this notation in this course many times. And sometimes you write this thing. Sometimes you write this as alternatively, again with a little bit notation, abuse of notation. You sometimes write this as this. And just because theta is what, and x and y are what you care about, after you know these three things, you can compute a loss. These are just some notations. Because we are sometimes going to use this notation, sometimes we use this notation a little bit exchangeably. So it's good to be aware of that. And you can define the so-called ERM solution, which is the arc mean of the empirical loss, and where theta is in this parameter theta, capital theta. And sometimes you just write theta hat as a shorthand for ERM. Like sometimes you can write this. By the way, you don't have to remember some of these kind of like cases. Just we're going to remind you later. So, and the goal, as you can expect it, is really again to show the excess risk of theta hat ERM is small, because that's the success kind of criterion, right? You want to show that you find some theta hat, and this theta hat is working, and working in the sense that the excess risk is small. And this is kind of basically the goal of the first probably a few weeks. And the core in some sense is really to, I guess, just a kind of like a trailer. In some sense, the core idea is to show that L theta is close to L hat theta, right? Because you are minimizing the L hat theta, but you care about L theta. So you have to show these two are similar in some sense, but it's not that easy.
The next question, the x for this should be in environment, right?
Sorry, this is I guess that is mean. Sorry, my bad. This is mean instead of R. Okay. Actually, I have a typo here in my notes as well. Thanks. Okay. So the goal is to show that your algorithm works, right? So and this theta hat this theta hat ERM is doing something, right? It's good. So and what does it mean by a model is good, right? A model is good it means that, like, at least in our definition, it really only means that the excess risk is small, right? Right. If you can make sure that you are kind of close to getting the best model in this family, then that means you are doing well. So that's why the goal is to show that the excess risk is small for this model. Eventually, you care about the learning algorithm, but to show this, it does depend on what the family of the hypothesis is. But the final goal is that you show a learning algorithm using this family of models can work.
Can you ever actually evaluate L, not L hat? Because I assume that requires control distribution, and you probably don't have.
So can you evaluate L?
Yeah.
Empirically, I guess. Yeah. So yes, you can evaluate L pretty well in the sense that you can have a holdout data. So that's why the validation data is used. Of course, there are some subtleties about Okay, so how do you evaluate L? So if you want, so the ideal scenario is that you collect some new data, and they are fresh data, and then you use the empirical estimator for it. The subtlety would be that whether you have seen this data before, right? If you haven't seen this data before, then you are all great. But if you have seen this data, then it becomes tricky. So that's actually exactly what we are doing here, because L hat and L, right? So this is kind of like intuitively very much correct, but the question is that this is we'll talk more about this. Like the subtlety is that whether you have seen the data before or not. Any other questions? Okay, cool. Okay, sounds good. So this is the kind of the main kind of topic in this course. Although there are gonna be more subtleties about this. For example, like in the first few weeks we're gonna talk about this, and then other things in this course. So we're gonna talk about how to, for example, one thing is how to minimize L hat theta, right? So suppose you know that all of this is great, but you still want to know how do you do this in a computational efficient way, right? That's something we're going to touch on for a few lectures, and also we're going to talk about kind of like additional complications in some sense in deep learning. In some sense, this framework becomes kind of questionable when you do deep learning. Of course, some part of it still kind of survives. Actually, most of the part survives, but some of if you really go into the low-level technical stuff, then some of the technical stuff stop kind of making sense, and there are a lot of additional complications, right? So so far, everything is still kind of okay, but then once you go one level lower, then some of the classical techniques don't apply to deep learning. And also, we're going to talk a little bit about unsupervised learning, which is kind of somewhat different, but still like some of these losses are involved, of course, and the generalization, all of this kind of like the notation still like mostly applies, but with a little bit differences. Okay, so that's the formulation. And now let's move on to like asymptotics, which before that, any questions? Okay, cool. So what does asymptotic analysis means, right? Asymptotic analysis. So this is a type of analysis where you assume that n goes to infinity. So let n, the number of examples, goes to infinity, and you show a bound like this of the form something like excess risk. This is our goal, which is L theta hat minus arc mean, sorry, minus mean. This is less than something like C over N plus little of 1 times small over N. And here, this constant C is a constant, but it's not a universal constant. It's a constant that, of course, doesn't depend on N. But could depend on the problem. For example, dimension. Right. So and the little of n is kind of like what you learn from calculus. This is like a lower term compared to 1 over n. So this is kind of the general kind of approach. And after we talk about this, I will talk about, then we're going to move on the so-called non-asymptotic approach, which I will discuss that after we talk about this. So okay, so shall we close door? I mean, I don't know. Could you be a little bit quieter? Yeah, I think that one probably is fine. Okay. Anyway, yeah, that's a good question. Yeah. So I think why we care about this kind of like a bond. So we want a bond that goes to 0 as n goes to infinity, because we want to say that if you have more and more examples, you can do better and better. But whether it's 1 over n or 1 over squared n or 1 over n squared, that depends on what's the truth, right? So it just turns out that the right bound is 1 over n, as we'll see. You cannot get better. You shouldn't get worse. Of course, it still depends on the setting a little bit, but for the setting we're going to talk about, 1 over n is indeed the right bound. Yeah. So cool. Okay. So now let's get into a little bit more concrete setup. So concrete. So I guess we're going to write this. Theta is RP. This is our family of parameters. And theta hat is, I guess I'm writing this again. So, but just to rewrite it, this is the ERM solution. And let's just, for notational convenience, let's define theta star to be the best model in this family, right? But this is the population risk, but not empirical risk. Theta star is the best in terms of the population. And our goal is to bound the excess risk, which will be just L theta minus L theta star. Okay, excess risk. So our goal is to show L theta minus L theta hat minus L theta star is small. So, okay, and I guess as a consequence of a trivial consequence of this is that L of theta star is the mean of L of theta. Okay. Yes. So okay, so here's the theorem I will prove. So I'm going to, typically in this course, I'm going to take this approach that we state the theorem first and then talk about why we want to prove it or how do we prove it. So we assume the consistency. By the way, this is like as with what I said in the beginning, this part of the lecture is a little bit informal, just because I don't want to get into too much jargon, too many jargons. So what does the consistency of theta hat mean? So this means that theta hat eventually converges to theta star in probability as n goes to infinity. If you're not familiar with what convergence in probability means, it doesn't really matter that much. So the reason why you have to have something slightly different is because this is a random variable. Theta hat is a random variable, right? If it's just some deterministic variable as a function of n, then you can define the convergence in the trivial way. But here, theta hat is a random variable. So technically, this means convergence in probability, just in case you are interested in this, but it's not that important. So convergence in probability means that if you take a limit as n goes to infinity, and you look at the probability of theta hat minus theta star is larger than some epsilon, this probability will goes to 0 as n goes to infinity for any epsilon it's larger than 0. But it's not very important for this course. Like for this course, it's perfect fine that you just understand this intuitively.
The theta hat is a random variable because it explicitly depends on the samples that are drawn for distribution that are.
Yeah, exactly.
So there's an assumption there that it's like the math for the samples that theta hat is like measurable or something like that, right?
Sorry, can I say it again?
There's an assumption that like the math from the samples of theta hat is measurable or something.
Sure, yeah, we have all of those, yes. Yeah.
When you were writing in landscape, the stuff was a bit bigger on the board.
Yes, but I think the issue is that it's going to be smaller vertically. So I felt that this is better, I think, because you have there's more things shown on the board.
Could you maybe write a bit bigger?
Bigger? Yes, sure, that's fine. Yeah. And maybe I should also repeat the question for the Zoom meeting as well, but yeah, next time. Okay, cool. So, and also this informally, like okay, sounds good. So, and then let's see. So, we also assume that the Hessian of the loss at theta star is full rank. And what does the Hessian mean? The Hessian is, I guess probably most of you have seen Hessian if you have taken CS229, but the Hessian is just the second order derivative, but you organize it in a matrix, right? So the Hessian of a function f is a matrix, and this matrix, all the entries are the partial derivatives like this. Right, this is a matrix of dimension p by p if f is a function that maps Rp to R. Okay. So, and there's also some other regularity conditions, which I'm not going to even state because like it's probably not super important for this course. And for example, this involves something like the gradient is finite, something like that. And under these assumptions, then you have that a few things. You can know a lot of things like about the theta hat. So first thing you know that is that formally you have to write this. So square root n times theta hat minus theta star. This is bounded. This OP of 1. So I'm going to define OP of 1 in a moment, but this is really roughly speaking just saying that theta hat minus theta star is roughly on the order of like 1 over square root n, something like this. So if you multiply theta hat minus theta star by square root n, then it becomes on the order of a constant. So what is this OP of 1 here? Again, this is not super important for the course. You can, if you don't think of it as constant, you can just think of it as O of 1, as in most of the standard CS courses. But the details here is that bounded in probability like xn as a random variable and indexed by n is OP of 1, this means for every epsilon that is larger than 0, there exists a bound M such that if you look at the probability that xn is bigger than the bound, this would goes to 0. I guess this for soup you can think of it as max. If you are not familiar with the soup, this is going to be very small eventually as n goes to infinity. But if you are not familiar with all of these jargons, just to think of this as O of 1.
One more question. The assumption that the hexagon is full rank, is that essentially similar to assuming that the minimizer is unique?
Yes. Actually, the minimizer is unique is already assumed when I define this in some sense. So again, I'm pretty informal here, but I'm already assuming that the minimizer is unique. But indeed, if the minimizer is unique, I think you need the Hessian to be full rank. But I think Hessian is full rank doesn't mean the minimizer is unique. Okay, sounds good. So, any other questions? But the most important thing here is that you somehow know how far theta hat is close to the star, and how far it is kind of something like 1 over square root n, and as n goes to infinity. And also you know that how different L theta hat, the population risk of the minimizer theta hat, is close to the population risk of the best model theta star, and how different they are. So they are different in this sense, where if you multiply the difference by n, then you get a constant, which pretty much just saying that L theta hat minus L theta star is something like 1 over n. Okay, so, and actually, you know more than this. So you also know that what's the distribution of the theta hat minus theta star. So theta hat minus theta star is a vector, right? So, and if it multiplied by square root n, it's going to be on the order of constant. But also you know what this distribution of this random variable is as n goes to infinity. I think this distribution is converging to a Gaussian distribution with mean 0 and some covariance, and this covariance is complicated. Let me write it down. Something like this. By the way, all of these are in the lecture notes, so you don't necessarily have to take notes if you don't want. Anyway, right. So like how to interpret this covariance? I think that's kind of like it's not interpretable for the moment, but the point is that it's a Gaussian distribution, and after scaling by square root n, so if you don't scale by square root n, it's going to be smaller and smaller. But if you scale by square root n, then it's going to be a Gaussian distribution with a fixed covariance, and it means 0. So theta hat is centered around theta star. So that's very good news. And also the fourth thing, you also know something about how different what's the distribution for excess risk. We have talked about the excess risk is as a random variable is on the order of 1 over square root 1 over n here, right? So this is what we have talked about. But also you know exactly what's the distribution. So the distribution is, it's actually complicated to state, but let me do it. So first you define a random variable. Let's call it a Gaussian random variable with some covariance. The exact detail here also doesn't matter that much, just because it's come from the derivation, right? You derive it, and you found that this is exactly the right thing. So, but the point here is that if you define this random variable, then you can know that excess risk, which is L theta hat minus L theta star, if you multiply that by 1 over n, then in distribution it converges to this random variable, the norm of this random variable S. S is a Gaussian distribution. And you also know what's the expectation of this if you really want, which is something like on the order of 1 over 2n. And you also know what's the constant. Okay, so all of these formulas don't necessarily matter that much because you derive it, you got this, right? But the point is that you almost know everything. So you know everything about L theta hat. You know the distribution of theta hat. You know L of theta hat. You know the distribution of L theta hat. It's very powerful. So and you can make all of this formal if you want. Any questions so far?
The first assumption is that a property of hypothesis space?
So is that a property of what?
What is consistency a property of? You can have two separate.
Yeah, so I guess my understanding is the question is that what the consistency assumption is that a property of something, right? So what property like is this the property of the problem? Yes, that's correct. So it's a property of the problem, meaning that it's a property of the model parametrization. Yeah.
Okay, so this might be the question. I have no idea how we went to this conclusion from the function. I'm not following what are some extra materials I can look up, or are these not very important?
Sorry, you are not following the why this is true?
For me to understand. So what are some other materials I can read?
I guess maybe we can talk about this offline. Is that okay? Yeah. Just come to me after the course. Yeah. Yeah, but you are not expected to, just one thing, like for anybody, you are not expected to see why these are true, right? These are just some statements saying that, okay, this can be done mathematically. I'll show you something about how to derive this, at least somewhat informally. And the proof actual techniques is pretty simple. The calculation is a little bit tricky. It's a little bit complicated. You have to work through it. But the fundamental ideas is very simple. Yeah, so far I'm only stating that these are all correct. Like you can prove all of this. That's the only thing I'm saying so far.
Are these the functions very strong, or are they like easily satisfied by any problem?
Yeah. So for example, the consistency assumption, right? Yes. So that's a very good question, right? So like so far we see this very strong statement. You know everything about theta hat, right? So some things probably should go wrong because otherwise we probably solve all the problems. There's no nonlinear assumption. It works for nonlinearity, right? So I think the problem is that the consistency assumption is a little bit tricky if you don't have n goes to infinity. Like you really have to have n to be really, really big. Then you can somewhat kind of like have the consistency. And I think basically the whole thing kind of like the whole problem of this kind of the limitation of this theorem is that you need to let n goes to infinity, and you really need very, very big n to potentially see this effect. So we're going to discuss this a little bit after we move on to the non-asymptotics, but the limitation, but yeah, that's a kind of like a trailer. Yeah. So right, so when you let n goes to infinity, you have super powerful tools in some sense. But still, like these are actually reasonable characterizations for many cases. So it's not like they are completely off the reality. I guess they are not necessarily that applicable to the modern practice, just because in these days we don't have n goes to infinity, right? Like you have 1 million data points in your image net, but your parameters is like 10 million. So n is not going to infinity as you fix the parameter. So that's going to be the next half of the lecture to some extent.
Are 3 and 4 different from 1 and 2, or like 1 and 2 are just consequences?
Yeah. 1 and 2 are consequences of 3 and 4. Yeah. And actually, when we really prove it, we are going to, if you do a very formal proof, you are going to prove 3 and 4 first, and then do 1 and 2. Yeah. Okay, I think I have 15 minutes, right? Yeah, I have 15 minutes. So yeah, okay. So what I'm going to do in the next 15 minutes to show a kind of informal proof for 1 and 2, and And next time I'm going to do a little bit more formal proof for 3 and 4, and then we're going to get done with this asymptotics. And then we move on to the more non-asymptotic stuff. Okay, so this is actually the proof, right? So the key of the proof is two things. One thing is you want to do Taylor expansion around theta star. And second thing is that you want to somehow use the fact that L hat is close to L and nabla L hat is close to nabla L. Nabla L hat is the gradient, the empirical gradient, and nabla L is the population gradient. And this is by law of large number. Okay, I'll elaborate on this. But I guess the most important thing is really the Taylor expansion, right? So once you can work in the neighborhood of something, then everything becomes somewhat easy. Okay, so now let's talk about how to really do it. So when you do Taylor expansion, so the starting point is the following. So you care about theta hat, right? So, and what you know about theta hat is that 0 is equals to nabla hat L. 0 is equals to the gradient of the empirical loss at theta hat is equal to 0. This is because theta hat is the minimizer, right? If you are at the minimizer, then the stationary condition tells you that the gradient is 0. But you want to relate this to L because everything is, it's easier when you do it with L because L is the population. So you somehow first relate this to theta star. So you want to relate everything, like basically the whole idea is that you want to relate theta hat to theta star and L hat to L. So the first thing is that we try to relate this to theta star. So you can write this as you Taylor expand around theta star. So theta star is a reference point. And then the first order term, this is the 0th order term, and the first order term will be the Hessian of the empirical loss times theta hat minus theta star. So this is the higher order kind of like Taylor, this is the Taylor expansion for multi-dimensional function, but it's exactly the same as one-dimensional case. It's just that you have to deal with some of the matrices. So maybe just a small remark here. So what I'm doing here is that I'm Taylor expanding something like gradient of G, Z plus epsilon, abstractly speaking. I'm going to do a lot of these kind of abstractions in my for small things, right? So suppose you care about this, and epsilon is your small thing, and Z is your reference point. You can show that the Taylor expansion for this is really something like nabla Z plus nabla square G Z times epsilon, and this is a matrix, and this is the vector. And how do you verify this? You can do this for like each dimension simultaneous, like individually, and you get this equation. It's kind of like intuitive as well, right? Because the Hessian is the gradient of the gradient. So this is the first order Taylor expansion. Okay. So now after any questions? Okay, so now after you do the Taylor expansion, then you know that this is the left hand side is 0, and then you can rearrange, right? So put this on the left hand side. So what you get is that nabla L theta star, theta hat minus theta star is roughly equals to minus, this is equals to minus gradient L hat theta star plus some higher order term. And then now you have theta hat minus theta star. You can take the inverse of the Hessian. So you have theta hat minus theta star is equals to the inverse of the Hessian times the empirical gradient at theta star plus higher order terms. Okay. Sorry, I that's my bad. It's still L hat so far. Thanks. Okay, cool. Okay, so and that's exactly the right point. So now I need to change all the L hat to L, and what I know. So I know that basically I want to kind of like change this to L, and I want to change this to L hat, to nabla L as well, and also I need to consider the kind of differences between them. So how do I do that? So I'm going to so at least I know a few things, right? I know that expectation of L hat theta star is equals to L theta star. I know the expectation of nabla L hat theta star is also equals to nabla L theta star. So you assume enough regularity conditions so that you can switch the gradient with the expectation, and you also have something like this. So, and this is equals to 0 because the theta star is the minimizer of the L, so that's why this is 0. And this is a P by P matrix, which is full rank, as we assume. So, and so basically this is saying, and also you can, because this is average of n IID terms, right? What is it? Because this is 1 over n times sum of nabla square L xi yi theta. So it's a sum of IID terms. Then you can use law of large number to say that this converges to this. And you also know that, okay, similarly, you also know that what I'm doing here, my bad. LS, this is converging to this. Okay, so okay, so if you want to just get the okay, and also moreover, by law of large number, you can also get something more kind of like accurate about this convergence. So here you are only showing that it's converging, but also you can know that how much difference they are. You know that if you look at the difference between this minus this should be on the order of 1. Or more accurately, this will be a Gaussian distribution with mean 0 and covariance nabla Li theta star. Nabla xy theta star. I guess this is because, if you, I guess I'm using central limit theorem here. Maybe I should first review central limit theorem. So when you have central limit theorem, you know that suppose x hat is equals to 1 over n times sum of xi, and xi are IID from some distribution D, and xi, let's say, is in D-dimensional. Then let's say sigma is the covariance of xi. Then you know that as n goes to infinity, you know A x hat converges in distribution in probability to the expectation of x. Right, that's the that's law of large number. I think that's called law of large number. And then the more accurate thing is that you can look at the difference between x hat and the expectation of x. And you know that if you scale the difference by square root n, then this converges to a Gaussian distribution. First of all, it's on the order of a constant, and second, you know the distribution is mean 0 and covariance x. And in some sense, this is saying that x hat intuitively, I guess, or informally, this is saying that x hat minus e of x is on the order of 1 over square root. Okay, so this is central limit theorem, and what we are doing here is that in this equation, what we are doing here is basically applying the central limit theorem, where you apply xi, it corresponds to the gradient of L at xi, yi. Yeah, this is the gradient of the loss at example I. Okay, so basically we have done some of these preparations. So we know that how different nabla L is from nabla L, nabla L hat is from nabla L, and also we know that the Hessian converges. And now we can come back to this important equation here. So and we are kind of ready to kind of get something real. So let me rewrite that. So theta hat minus theta star, this was nabla square L hat theta star inverse times nabla L hat theta minus nabla L theta star. Wait, sorry, is that right? No. Copy. This is not nabla L theta star hat plus higher order terms. So this one is close to nabla square L theta star inverse. That's the first thing we know. And also we know that this one is roughly speaking nabla L theta star plus some 1 over square root n. Right? So suppose you do both of this, then you get something like and this is roughly equals to 0. So then you get 1 over square root. Maybe I'll ask the question first because this takes a little bit of time.
I'm just going to ask if there was any difference between x hat and x. That's a little bit.
Can I say again?
Is there any difference between x hat and x in your statement of the central order theorem?
X hat and x. Oh, sorry, my bad. Wait, why? Oh, I guess yes. So I'm thinking x is also drawn from D. So maybe I should either use xi or let's say x is a generic variable that is drawn from the same distribution D. But the expectation of x is the same as expectation of x hat. That's right.
Question? Are we missing a minus sign there?
Here, right? Is that okay? Yes. Yeah, I'm missing that. Okay, so maybe like I'll just do this a little bit more carefully. So I'm basically trying to kind of replace the L hat with L, right? So the first thing is that the gradient this I guess using this equation, maybe let's call it 1. So this is roughly equals to 1 over square root n plus nabla L theta star, which is 0. So this is roughly equals to 1 over square root n. So if you don't care too much about the vector versus real number or the distribution, then you get 1 over square root n. And this one is kind of close to a constant. Inverse converges to, which is a constant. So that these two things together will give that, maybe I see the yellow color to continue, so minus something like 1 over square root n on this order of 1 over square root n. So something like maybe more explicitly, you get nabla square L theta star inverse times 1 over square root n. And this is on the order of 1 over square root n. So that's how you get that theta hat minus theta star is on the order of 1 over square root n. Of course, this is not, just to clarify, this is not exactly formal because I'm ignoring a lot of things. For example, this is a vector. This 1 over square root n is really a vector. It's not a scalar, but it's on that order. So that's how you get that theta hat minus theta star is on the order of 1 over square root n. And also heuristically, if you really care about L theta minus L theta star, then you can, this is the excess risk. You can also do the Taylor expansion. You say that this is, you Taylor expand around theta star. You get that this is L theta star times theta minus theta star. Sorry, this is maybe wait, why I have so many typos in my notes? Sorry, my bad. So this is theta hat. This is the, okay, so plus. Here, the interesting thing is that if you do a first order Taylor expansion, you're going to get 0. So you'll have to do second order Taylor expansion. So you're gonna get theta hat minus theta star times Hessian plus high order terms. Okay, so the reason why I need to do the second order Taylor expansion is because the first order Taylor expansion is 0, because this is 0. Theta star is the minimizer of L, right? So that's why we have to look at the second order Taylor expansion. And if you want to roughly see how large the second order Taylor expansion is, you can see that each of this term, this is 1 over square root n, this is 1 over square root n. So basically, the second term will be something like 1 over n plus high order terms. Okay, so this is a some kind of heuristical proof to show why say the hat minus the star is on order of 1 over square root n, and in terms of the loss is on the order of 1 over n. Any questions so far?
So consistency is needed for the
Yeah. So consistency is needed in almost every step. I'm using the central limit theorem on the random variable, not a function of it, because I'm not sure whether that's like. By the way, I forgot to repeat the question, but anyway, I'll remember that next time. So the question was that whether the central limit theorem is applied to the random variable itself. I think so, because xi is this xi, right? So that corresponds to the gradient. So gradient of L at that example I is my random variable. So that's how I got. So and then the sum of xi, this corresponds to the empirical gradient, and right. So and the expectation corresponds to the population gradient. Does that make sense?
So I think would you need some constraint on gradient as one go on something that you need to.
Yeah. I think you need a lot of like different kind of like regularity conditions to make all of this work. Because for example, also there's an implicit step that I didn't go through, which is the inverse, right? So like I only show that the Hessian is converged to, for example, where I did that. So I only show that the Hessian converges the empirical Hessian converges to the population Hessian. You also need to show that the inverse of the empirical Hessian converges to the inverse of the population Hessian. So that's another thing you want to formally deal with. So yeah, every time I give this, like I've taught this like 2 or 3 times, and every time there are a lot of questions about this first lecture. I still haven't figured out a better way to teach it, but I think maybe the thing is just that, like I really want to convey this idea. Like the idea is that you can do Taylor expansion, and you can pretty much do a lot of heuristical stuff, and all of them can be made formal. And how to exactly make it formal is a little bit tricky, as these are all great questions, right? All the questions are welcome, but just to set up the expectation, this is not meant to have a very formal derivation here. Okay, so I think that's all for today. So next time we are gonna make this a little bit formal, maybe for 15 minutes, and then we're gonna move on to other things.